Hello community, so great that you are back. We have some brand new AI research regarding reasoning and knowledge in our transformer architecture. And you know this, we have been there, no? You ask yourself, hey, did the LLM just fail because it lacked the necessary knowledge, the reasoning capability? Or did the LLM fail because it simply failed to reason correctly with the parametric knowledge it possesses, and I just have to apply here graph reg optimization? Now, to come up with a solution, we have a brand new research, and they said, you know what? We do a simple experiment. We do a fast thinking where we say to LLM, hey, your output is exactly only one letter. There's no reasoning, there's nothing, a question or additional text or punctuation, just one character. You want to have the direct access here to the LLM response based only, if you want, on the parametric knowledge of the model. So if you want, this AI has now a gut reaction based on its most immediate high probable patterns stored inside its tensor weight structures here of the layers of the transformer. And we get an immediately accuracy of this model. Let's call it A for accuracy, the fast thinking model. And this becomes our direct quantitative measures of the knowledge retrieval capability. Now, of course, we have to go then with the chain of thought deep reasoning process. So we do have here a prompt for a slow thinking. You can use this, of course. And what we get, something, because we have to evaluate this. So we use another LLM, a GLM4+, to evaluate this here. Great. We also get an accuracy here. Let's call it A slow for slow thinking. It represents the final outcome after both the knowledge retrieval and the deep reasoning have occurred. Now, the authors of today's study said, okay, let's do this with different models. We want to see different models. No? So when they write Q1, it's a Q1 2.5. If they go with QWQ32B, it is a 32B preview. With a llama, it's a 3. Gamma is still a 2. Phi is already a 4. So great. You have the classical models that we have, and we go with the classical data sets. So we have a lot of data, so no problem. We have enough quantity for our analysis. And the author said, let's look at first at the token consumption of our LLMs. And you see here the token consumption of a Q1 1.5B to a 32B, independent if it's correct answer and incorrect answer, it is actually surprisingly here within here a very close interval of tokens. But other models, like if you move from a Q1 to a QWQ, you see, hey, wow, it can suddenly double. Very interesting. I, for example, thought that a llama 1B or the llama 70B, to deduct here the correct and incorrect answer, the amount of token consumption would be different. Turns out, no. Look, it's almost the same. And then he said, what about domain-specific knowledge? And here on A, you have mathematics, and here on B, you have medical. Interesting, look at this. The result demonstrates clearly that mathematics here, our A, imposes a higher demand on the reasoning, and you see here the slow reasoning here in orange, than the reasoning here on medicine. Now this is interesting. So there's something happening. Now, there is now a difference we have to examine, because why is it that if we have the fast thinking compared to the slow reasoning here of the same model, this is just here the model size increases here on the x-axis, but you see, in general, we have an identical trend that there's a vast amount of difference between system 1 or system 2 thinking. Completely different in medicine. Why is this? So let's have a closer look. Now, they also noticed, hey, we just want to tell you there's what we call an anchoring effect. Now, we know this anchoring effect here from humans, but you know what? Funny. There's a funny fact that is also happening here with AI systems. So if you have a question, let's say we go with a multiple choice and you know A is the correct answer, and then we just disturb here a little bit the AI, no? Or maybe you just bring it in from RAG, no? And there's another piece of information and it gives you here an idea. The correct answer seems to be B, but I don't really know. So you know you have kind of a predisposition here, information brought in context learning RAG systems, and now this anchoring effect. Is it also happening here with our latest AI model? And look at this. This is unbelievable. So again, we have a model size from 1.5 billion free trainable parameter to 32 billion. And what we have here anchor, without an anchor. So without this here, the correct answer seems to be B. And then we have the difference here in the performance. Yeah? So let's have a look here at the performance data. You remember this is the fast, if you want, thinking and the very slow deductive thinking here in a chain of thought. So you see, if we have given an anchor to the LLM, the performance is not really famous, no? 8 points. But without an anchor, so without this here, the system thinks, oh no, it has a little bit of inherent knowledge and completely has a different performance of 39, which is great. Now, if you take the difference, you see anchor minus without anchor gives you minus 31. Now look here at the, if you want, system 2, the slow thinking model. Yeah? If you provide it with an anchor, okay, you have an effect if you compare it to without an anchor. So you only achieve here a performance of 40 compared to 62 without an anchor. So in general, if you compare here now the slow thinking to the fast, give me the answer immediately, there is a significant performance difference. Yeah? But it also shows you here, if you just take here the difference, that here the fast system is much more sensitive to anchors. And if you increase this, you see, interesting. So the effect on fast stays more or less the same, no? Minus 26 at a 32B compared to minus 31 and a 1.5B. But look, if you go here with the slow, the effect of anchoring is much less massive here because the system has, if you want, a causal reasoning regime that it tries to follow and come to a conclusion. Interesting. So the anchor minus or without anchor indicates here the accuracy decreases due to anchoring. So we have a massive bias. And the performance decline in slow thinking is generally less. You see here the blue line here, the blue numbers here. In general, less severe, indicating that reasoning adjustment effectively mitigate here the anchoring effect. So we have to take care about this. Great to know. But you know, this difference here, this is the delta we introduced, a new parameter, almost forgot to introduce it to you. So fast and slow, and you see the difference, the delta is exactly 32, and you get the idea. Great. Now, what they did, they said, hey, this delta is interesting, but you know, this delta here, and if we do it now here for a lot of different models, we can have a look at this, but there's also a deeper symmetry within the delta. There are other components in this delta if we have a mathematical look at the factor delta. So delta is not a monolithic quantity. It is kind of a net result of a tug-of-war between two competing cognitive forces within your LLM. We have a delta C and a delta O, a delta correction and a delta overthinking. And then we have a normalized rate. So let's have a look here at the mathematical formulas just for a second. So the delta, without going into any details, has here a delta C, a delta correction, and a second term, a delta overthinking. So it tells us here, hey, having a look here at the mathematical background, it shows us here that the reasoning adjustment, we have two effects. So the LLM corrects the error made by the fast thinking, but it also incorrectly overrides here the correct answer it found. So we have a positive effect and we have a negative effect. And now the question is, what is the net effect in total? And they said, yeah, you know, we have also here to look here, if you want, at the rate of correction and the rate of overthinking, if we normalize it, because we want to have here a real precise parameter. So again, what we have a delta C and a delta O. The delta C is, if you want, the correction gain. This is the value generated here by the reasoning of the LLM. This is the fraction of all the questions that were initially wrong, but were corrected now by the reasoning process of the LLM. And this is great, so we improve our performance. But at the same time, the authors found we have a negative effect, an overthinking loss, gain and loss. So this cost, if you want, a course now, also by reasoning. But this is not a fraction of all the questions that were initially answered correct by the LLM, but were later on corrupted into an incorrect answer by a non-optimal reasoning process. The LLM just decided, okay, I don't know if this is a correct answer, so I reason about it, and it turns out it reasons to an incorrect answer. So the net reasoning gain of these both effects is, if you want, profit minus loss, is our delta. So you see, delta is not monolithic, but has components. Now, what is the rate, this correction rate? I can call it, I want to call it here reasoning intelligence, né? Because given that the model's initial intuition was wrong, you ask now, hey, what is the probability that this LLM reasoning will now fix this initial mistake that intuition based only on the parametric knowledge base? And here we have your RC, so the correction rate here, the probability, is now a simple mathematical formula. And also we do the same for the overthinking rate. Né? Let's call it the reasoning recklessness. So given that the model's initial intuition was correct, you ask now, hey, what is now the probability it will continue to overthink this and therefore break the reasoning process and arrive at an incorrect answer? And we get here also a simple formula for this. And now the interesting fact is those rates are important factors that tell us a lot of the behavior of the model. Because this decomposition that we have of our delta into the rate and into the two factors is now incredibly revealing if you read this new paper. Because now it explains why small models often fail at the reasoning. And I thought, hey, it fails of the reasoning because those are models rather small, a 1.5 billion model. Ne? Now it turns out that there is a very particular effect if you have this decomposition of delta. It means that there are high rates here of, let's call it, recklessness, swarms their intelligence, leading here to a net negative delta. On the other hand, for the large language models that achieve here a superior reasoning performance in general, this is not necessarily by being dramatically more intelligent, quotation mark, as an LLM, but there's an effect taking place. But by becoming vastly more cautious, more prudent, their specific rate on overthinking drops abruptly with the scaling. This is now a new insight. This is now something, looking here, all the data I already showed you, this is something interesting that they found. Let me give you an example. This is my example. This is not official. This is just my internal thinking. Maybe it helps you. Maybe I made a mistake. Please, the small model, an 8B model. Né? Let's say our accuracy for the fast reasoning or fast thinking, the mode 1 or thinking 1 mode, is 60%. So it knows the answer 60% of the time. Now the intelligence rate, if you want, no, it has a decent correction rate, let's say 40%. So it can fix 40% of its initial mistake that it made during here the fast thinking. Now talking about prudence here, it's not very prudent. Yeah? It has a high overthinking rate as a small model, let's say 17%. Go with whatever model you like. So it gets tempted to change its answer, and 70% of the time it correctly knew the answer, but it ends up breaking it through here an incorrect flawed reasoning process. So we have data, 60%, 40%, 70%. So let's do this now on a real world example. Let's calculate the reasoning gain delta on a 100 question test set. So what are the gains from the intelligence that we have? No? So on 100 questions, it's wrong about 40 questions. So it fixes 40% of them. So we have 16 correct answer with the, if you want, additional gain here from the intelligence. But we also have, as I told you, a counter effect. These losses from the imprudence. No? So it was right here on 60 questions, no? 60, 40, 100. But it overthinks and breaks 17%. So this means we have less than 10 correct answers. Now, what is the net reasoning gain that we achieved? Yeah, not going to believe it. 16 minus 10 is exactly 5.8. So reasoning is helpful here, but its benefit is significantly blunted by its tendency to self-sabotage, self-correct itself, but in an incorrect way. So this is now interesting that we have now this specific data on the Llama 3 model. So it is really interesting to know here the rates, the gains from the intelligence and the losses here from the incorrect corrections. Now, the situation is different at the large model. Let's say we have a 70 billion free trainable parameter model. No? And let's say here the accuracy of the fast thinking here, the system 1 thinking is 81%. It's really good. Now let's have a look here again at the intelligence. No? According here to the paper's data, its intelligence is not dramatically higher. In fact, actually it's 38%. So its raw ability to fix a mistake it doesn't know the answer to is roughly the same. And remember, in the smaller example, it was 40%. So it's now even slightly lower. But look at the prudence. No? This is where everything now changes. Now, this model becomes vastly more prudent, more cautious. Its overthinking rate plummets now to 7%. So it is now, if you want, much more stable in its reasoning performance, and it is less likely to corrupt here a correct answer and modify it into an incorrect answer. And you might say, okay, so what is the net effect? So let's calculate this. So again, we have a 100 question test set, now with a Llama 3 70B model. Again, gains from intelligence plus 7, losses from imprudence here minus 5.7, and the net reasoning gain is now plus 1.5. And I looked at this and said, what? How is this possible? How is it possible that a big, more powerful reasoning model, let's say it is a reasoning model, has suddenly less net reasoning gain? The delta for the Llama 70B model is 1.5 and therefore smaller than for the small 7B model. How is this possible? No? Because normally I would assume that a large language model reasoning process is far more reliable and efficient. Shouldn't it result in higher gains? And then I noticed that I made a mistake in my reasoning, in my human reasoning. The 70B model reasoning gain delta is smaller precisely because its initial knowledge, you remember, the accuracy of the fast thinking, is so much higher, 81%. So it has already solved most of these easy and medium difficulty problems, no? These low complexity levels, no? Using its, if you want, type 1, its fast thinking mode. So the pure knowledge retrieval system. So the reasoning process now, the system 2 thinking or whatever you want to call it, now is left to tackle only the most difficult complex problem where the potential for an error is high for any process. No? So the potential for large gains has been indeed diminished by its own superior baseline performance. And now I have a personal idea. So you see here me starring ideas, and I have just want to tell you, hey, I think that in the 70B model, the knowledge and the reasoning data encoded representation in the transformers are not two separate anymore, are not two separate clunky modules anymore. No? Somehow I have a feeling that its vast and robust knowledge base of a 70B model or a bigger model, no, reflected here in the high A fast performance accuracy, already contains here implicit reasoned out patterns in its pure reasoning structure. So what it means, I showed you here, if you especially do a distillation process from a teacher to a student model, I showed you we don't just have fact base, but we take the reasoning traces from a DeepSeek R1, we extract the reasoning traces, and those reasoning traces become now the pre-training data sets for the smaller student model. So it's not just that we say we have pure data and pure information. We also have knowledge that is implicitly reasoned patterns. So this means the distinction between what is pure knowledge and what is pure reasoning, I don't think it's really that massive here when we scale the models up to higher model sizes, and especially if we have these distilled models. And I think its fast thinking is so good because it requires less slow thinking correction, because on the reasoning traces that it was trained on, there is already here a pattern that provides a solution to the complex problem. But this is here my personal statement. You see here me looking at this. Coming back to the paper. So they say, let's focus here not on delta, let's focus here on the normalized rates. And they say this is the key takeaway from our study. So to compare the intrinsic quality of the reasoning process itself of an LLM, we should look here at the rates here, RC and RO, overthinking, which normalize for the baseline knowledge. Now this makes sense, no? Now, also now, I think the 70B model reasoning process is far more, if you want, reliable or efficient, not because it produces here a larger delta, which it does not, as we just saw, but because it achieves its result with vastly less self-sabotage, this ratio of overthinking. It is much less. So it is a more stable reasoning pattern machine. Its reasoning processes, its flow is much more precise and targeted and more elaborated. It is not just jumping around and self-correcting it whenever it thinks it's possible. That's a more stable, more advanced model, a 70B model, in general. So now an interesting question for you, my audience. Is it that a primary function of scaling up a model, is to create a more robust and stable internal world model for this particular LLM? And remember, world model, reward models, reinforcement learning, yeah, exactly this is where we are. So that it is less easily perturbed by the noise of its own thoughts. Is this really the main fact that distinguishes here a small language model from a large language model? Especially its system 1 thinking and system 2 thinking? Is this the main effect? Well, at least the paper showed us that the reasoning is not monolithic. It's not a parameter in itself, no? It's a contextual relation. So the framework that we show here proves quantitatively that the reasoning benefit, our delta, is highly domain dependent. I'll show you an example of mathematics and medicine. Huh? It's massively positive in mathematics, but it can be negative in a knowledge-intense field, let's say history, if the underlying parametric knowledge base of this particular LLM is weak, of course. But easy, no? If we have if you want, not so performant knowledge base, we know we can help here with graph rag optimization. So we come now closer to the question, what should I do if my model is not performant? Should I activate graph rag, or should I continue here with reasoning traces? And the answer is, yeah, but before I give you maybe my answer, there was another question the authors had. And they said, hey, can we maybe pinpoint the exact location in a transformer layer where this is happening, what we just found? And they have another parameter, well, of course, but it's a simple similarity measure between here, type 1 and type 2, between fast and slow thinking. And so this CKA is calculated here for each specific layer in our transformer between the two modes of fast thinking and slow thinking. How you do this? It's a simple metric. Here's the calculation for you. Great. But what is here the main idea? And yeah, maybe it's a good idea to introduce you here to the main paper. This is here by Tsinghua University here from Beijing in China. This is here published July 24, 2025. A beautiful paper. It gives you a lot of factual data, but sometimes it leaves open the answer to the main question that I, for example, have. But really interesting paper. Have a look at this. And the authors, they say, listen, we have the starting idea from the human that we have a dual system cognitive theory also for LLMs, which I would say is a stark idea to start from. But okay, let's go with their theorem. And they say this dual system cognitive theory, which decomposes here the LLM inference, into two distinct but complementary phases. No? And they say an LLM also has here phase 1 and a phase 2 thinking. Phase 1 is now the knowledge retrieval, where the LLM rapidly generates here an initial response by accessing here the learned information. And I showed you at the very beginning of this video the prompt for phase 1 and the reasoning adjustment. This is the phase 2, and I also showed you the prompt for the phase 2, so you can experiment with this. And they say Here's where they refine here the initial responses through a chain of thought generation or whatever you have. So knowledge retrieval from its parametric knowledge without thinking too much is phase one of the LLM. And if you start here, you know, this typical think step by step and validate and react and retract and everything. This is not a reasoning adjustment of the LLM. This is what I call here the phase two of an LLM. If we can map this really from a human brain to an AI, I would put a big question mark behind this, but let's go with this. And they argue here to separate the two cognitive phases of an AI systems. No? The LLMs are now simply prompted to generate answer under the two distinct cognitive modes, the fast thinking and the slow thinking, and you have seen already the prompt at the very beginning of this video. And they think now the difference between the cognitive mode is analyzed now, and they found it is a kind of a decoupling of knowledge and reasoning. And especially the reasoning is further subdivided, so the reasoning adjustment, as they call it, is now decomposed here into the correction, our delta C, and the overthinking, our delta O, or the rate of correction and overthinking. So this is their assumption which they are working with. If it's the absolute true model, But interestingly, their approach provides us more information analyzing here the limitation of small model reasoning. Why do small LLMs fail so massively on the reasoning process? And their answer is it's not because they are so small, so they are incapable of reasoning. But they say here, if we look at the reasoning adjustment that is happening with a small LLM, you have two forces within this. Yeah? So you have a correction force here, but you also have an overthinking that kind of destroys here the performance. But this overthinking is so much more dominant in small model reasoning, which would give us an idea how to optimize those small models, especially here on the overthinking problem that I was not aware at all. So if we go with this hypothesis that LLM also generate answers like human in two phases, no? LLM retrieved memory knowledge and LLM applied chain of thought reasoning, beautiful. I don't know, this underperformance now applied here to this thinking, but let's go with this. So fast thinking is the knowledge retrieval and slow thinking is the reasoning adjustment. Great. And they have some beautiful thing here. And yes, we already went through the formulas. What are the insights? This cognitive hierarchy, indicating that the knowledge retrieval and the reasoning adjustment operate at different hierarchical layers within a neural network, is kind of what we already know of. Yeah? But they made it more quantitatively easy to check. And this is a nice aspect. And of course, they have a new parameter they call here the centered kernel alignment here. This is simply here a measure of a neural network alignment, a similarity, and here you have it. A and B. Here we have a Q17B, and here we have a Llama 8B, so real close here in the size. And you see if we have on the x-axis here the number of the layers, over 30 layers, you see here this new parameter. So this, remember, this is a similarity parameter, and a lower CKA, below 1, going down here, as you can see, indicates reduced similarity for the given layer that they examine. So as you see here, all CKA curves here exhibit an initial plateauing, if you want, here in the lower layers, followed by a decline here in the higher layers. We see this here for this model, we see this here a little bit less for this model, and all the data sets that I told you at the beginning. So this is an interesting phenomenon. Eh? What does it indicate? It indicates that the lower layers here remain similar across our thinking modes, while here in the higher layers, in the later layers of our transformer architecture, we have more divergence in the similarity. And you know, we have an idea already that in the last layers of a transformer architecture, the real reasoning is happening. So this would mean that here the phase one or the slow thinking would happen here in the first, let's say, 20 layers. If you look here, no? This is almost a plateau. And they say, yeah, this suggests now that both modes share the knowledge retrieval here in the lower layers, but the slow thinking additionally engages here a reasoning adjustment in the higher layers, and this is why we see suddenly that our CKA parameter goes down. The similarity measure is reduced significantly. So they say our results suggest the knowledge retrieval and the reasoning adjustment are primarily localized to the lower and the higher layer. So knowledge retrieval, lower layer, reasoning adjustment, the higher layers only. Interestingly, so see those performance indicators here on the different levels. So what does it mean now for a typical AI scientist? It means we have now a tool set for a targeted intervention. We open this video with a question, hey, why the model is not working? Is it because the reasoning capability is not given a complexity level that I want to solve? Or is it simply, it has not enough facts about it? And they tell us now a knowledge deficit calls for continual pre-training, or we need GraphRag. So we have to provide additional data, new knowledge. They say, however, if we discover that it is a reasoning deficit here in the performance of the LLM, this calls now for supervised fine-tuning, or further, if you want, chain of thought, reasoning trace distillation from a much more potent model. So this is an interesting insight now, in addition to everything, that now if something is not working, we kind of have now a tool set, and they tested it only here on a Llama and on a QN 2.5, to have here a further understanding why this LLM is not functioning. And if we understand why, we can take targeted actions. We don't waste anymore any compute cycle on the wrong fixing of the problem. So, interesting study, kind of a knowledge we already knew what's happening. It kind of explains in a new way why smaller reasoning language models do not have the performance like an LLM. It is not in the scaling itself, but it is also here in the particular overthinking process that a smaller reasoning model here simply destroys already correct answers. Absolutely amazing insight. Have a look at the study, you're gonna enjoy it. If you like this kind of videos, subscribe, and I see you in my next one.